Hello, welcome to my talk on my wafer paper, Efficient Contact Mode Enumeration in 3D. My name is Eric Huang. This work was done in collaboration with Xianyi Cheng and Matthew Mason. This was done at the Carnegie Mellon University at the Robotics Institute in the Manipulation Lab, and this work was funded by NSF. To begin, contact modes are a tool for programming robots which have to make and break contact. So this type of robotics is commonplace in robotic manipulation and in robotic locomotion. Contact modes are a useful way for describing and enumerating various motion primitives that are applicable to an object. Each contact mode maps to the dynamics, a region of smooth dynamics for the object. So they're useful for the analysis and control of during manipulation. They're also useful for planning and sequencing of various actions. This paper contributes to the theory and computation of contact modes. So we discuss how to go from a particular environment or scene, how that generates a certain type of geometry in the velocity space, which leads to various different contact modes, which have a lattice structure. We tend to think of manipulation in terms of primitives, such as these various types of grasps visualized here. Our viewpoint is that contact modes are a tool for programmatically describing manipulation primitives. So the numbers that or the strings that I've written next to each of these primitives represents which fingers are actively contacting the object. So we'll jump into defining how contact modes work. So a contact is either contacting or separating. So on the left, we have a contacting contact or maintaining, and it's not moving. On the right, we have a separating contact. So this object is being lifted and the contact is broken. For a non-separating contact, that contact can be classified as either sticking or sliding. So on the left, we have sliding. So the bottom left corner of this block is sliding across the ground as the robot manipulates it. On the right, we have sticking contact. So that bottom right corner is not moving during the manipulation. We can write contact modes as a mode string. So this string is +0+, and we can partition it into the contacting separating mode and the sliding sticking mode. So here, the contact on the right is separating. So the mode is plus for separation. The contact on the left is technically sliding. So it's maintaining contact. So the contact mode is 0 in this case. The particular sliding sticking mode for this contact is plus because it is sliding to the right. Now this also generalizes into 3D, which we discuss in the paper. Contact modes are useful because they enumerate the various smooth regions of smooth dynamical manifolds. They sort of are the discrete component of contact dynamics, and each discrete component comes with a continuous component. As we've taken a figure from a ICRA paper that does a good job of visualizing all the different types of modes, discrete modes, and continuous manifolds. This could be useful for control, as a robust control policy must be able to handle all the different contact modes. In other words, all of the different types of dynamics that the robot may undergo. In this video, we see big dogs slipping over ice and experiencing many different types of contact modes in the process. In this video, we take a look at the various possible failure modes for a single action, which is intended to slide a block to the left. As you can see, there's many different ways that the block different contact modes that could be executed, but we only want one of them to be executed. And so your controller must be robust to these different types of failures, which are captured by this idea of different contact modes. Contact modes also describe the tangent spaces during object manipulation. So in this case, for manipulating this block on a table in 2D, these are all the different types of motions that we can generate involving this block. And these different primitives are captured by different contact mode strings. We'll talk a bit about our contributions towards understanding contact modes as in terms of their geometry. And so when it comes to a particular contact, the various contacts, each contact defines a normal velocity inequality constraint. That is, for instance, this contact on the right states that under the rigid body assumption, we cannot be penetrating. So this contact point cannot be moving into the ground. It can only be moving, it can only be staying on the constraint manifold, which is the ground, or it could be lifting off. And this idea is captured in the object's twist space by a half space. And we've shown this half space equation here alongside with a visualization of that half space as a hyperplane. The sphere in the center is also for visualization purposes. So if we add in the other contact, we now have two half spaces whose intersection defines the region of feasible velocities. Now, each contact also defines tangent velocity directions that you could be moving in. In this case, for a 2D example, the contact may be sliding to the right or to the left at the contact point. And this idea is captured by another hyperplane in twist space. So in this case, if you're on one side of the hyperplane, if you're above the hyperplane, you're sliding positively. If you're below the hyperplane, you're sliding in the negative direction. It just so happens that both these contacts, their tangent directions generate the same hyperplane. The regions carved out by these various hyperplanes are the contact modes, which we've visualized this block sliding around these different contact modes. We've demarked each region by a black dot, and when that dot turns purple, that's to indicate that we're moving in this particular mode at the moment. This is useful because we can use contact modes to guide manipulation planning. For instance, in this work, we used the various contact modes to help us plan a sequence of different actions in order to lift and flip this heavy object. And as you can see, we're transitioning between contact modes, performing sticking contacts and sliding contact modes. We have some additional examples which demonstrate this idea at work. And this is enabled by our wafer paper on contact mode enumeration. For instance, unpacking a blocks in a tightly constrained space, pushing a block up a cliff. It has the transition between sliding along the ground and then sliding up the cliff, or just going over an obstacle course. In this paper, we also show that contact modes have a highly organized lattice structure, and we've depicted this lattice structure on the right. The various nodes or vertices, the nodes in this lattice structure correspond to various faces of different dimensions in this in the hyperplane geometry of these contact modes. So for instance, the lowest level corresponds to the zero-dimensional faces, which we'll call vertices. The one-dimensional faces we'll call edges, and the two-dimensional faces we'll call faces, and so forth. The d minus one-dimensional faces we'll call facets, and so forth. The lattice structure also, for completeness, just has a unique maximum minimum, which corresponds to an empty set versus the whole space. And the lattice has a partial order by inclusion. So the vertices include the empty set, obviously. Each edge will include two vertices. Each face will include some number of edges. When you put it all together, you have the full lattice structure. Now there's only some contact modes which are feasible under the rigid body assumption, aka meaning no penetration, and we've highlighted the ones that are feasible and grayed out the ones that are infeasible in this case. So every set of contacts generates a hyperplane geometry, which in turn has a combinatorial structure, which is the contact mode lattice. And if we play this video again, we can see that different motions of different dimensions are part of this lattice. So in the vertices, they have the least amount of degrees of freedom. The edges have just one more degree of freedom. And then the faces have the most degrees of freedom. This type of information is useful for planning a sequence of contact modes. For instance, in robotic locomotion, an old paper from Aaron Johnson in 2014 searched for a jumping trajectory by moving through this lattice. Now they created their lattice by hand. Our work enables us to automatically generate this lattice for any type of contact configuration programmatically. So in this paper, we've proposed the first contact mode enumeration algorithm, which works in 3D and for multiple objects. There really are only two previous methods which work in 2D, do not handle multiple objects, which we've listed here. Our enumeration algorithm for contacting separating modes is based on taking a convex hull. And for those who have been exposed to this before, we generate the convex polytope corresponding to the normal velocity constraints, and we use the polar transform to turn those hyperplanes into points, which we can then take the convex hull of. We generate the sliding sticking modes using an iterative Minkowski sum. Basically, for every hyperplane, we iteratively add their normal directions and expand a particular polytope called a zonotope, and we can construct this using many convex hulls. Our enumeration results show that contacting separating modes are much faster to enumerate than sliding sticking modes. And here we have some examples of our enumerated contact modes visualized in this video. So this is a box on a table, and we are visualizing all the different ways a box can slide or stick on this table while maintaining all 4 points of contact in this particular segment of the video. At the top left, we have the contacting separating mode lattice, and on the bottom left, we have the sliding sticking mode lattice. For the contacting separating mode where all 4 vertices are on the table. Next, we show the contacting separating modes for a box against 2 walls. We don't show the sliding sticking modes here because there are too many to run through. As you move down the ranks of this lattice, you get progressively more and more degrees of freedom available to you. In our next video, we show a hand grasping a football, and we just show example contact modes from each rank in this lattice. Again, as you move down this lattice, you get progressively more and more degrees of freedom. Okay. To recap, contact modes are a tool for programming robots which make and break contacts. They're a interesting theoretical tool for helping you classify various primitives. They divide the space of the dynamics into locally smooth regions. And we've seen how they can be useful for sequencing manipulation actions together. This paper contributes to both the theory and computation of contact modes. We describe the geometrical background behind the contact modes, and we show how we can compute them using well-known algorithms such as the convex hull. Thank you for listening.